So this last problem is probably easier to do using relative velocity, but we'll solve it both ways and see if we get the same answer. In this case, we know that the velocity of c is the velocity of b plus the velocity of c relative to b. What do we know? The velocity of b is b, and it's actually spinning around a with 10 radians per second, and its distance is 2.5 feet, no, 0.25 feet. So r omega equals 2.5 feet per second, and it's going clockwise, so this velocity is going up like that at 45 degrees. Velocity of c relative to b, it means c rotating about b. We pretend b is fixed. There's c. It's rotating counterclockwise, so that one's shooting back like this. Okay. And the r was 0.75 feet, and the omega was 2.43 radians per second, and omega times r equals 2.43 times 0.75, 1.823 feet per second, perpendicular to that arm, which means it's at 13.6 degrees above the horizon. Okay, and so hopefully that will all add up to C having a vertical velocity. So velocity of B. Okay, 2.5 at 45 degrees plus the velocity of C relative to B. It's 1.823 at 13.6 degrees. Okay, I'm going to add the x components and add the y components and come back. Okay, so I took those vectors and got the sines and cosines, and something's wrong. I have to go find this problem, but look at this. So 2.5 cos 45 degrees is 1.313 to the right. 1.823 times cosine 13.6 is 0.933 to the left. They don't add up to 0, and the picture shows the piston going straight up and down. So there's something wrong with the numbers. I double checked everything I've done so far and it was right. It's not right. I think it must be asking something like, oh, that angle can't be right. What is the angle so that this thing is going vertically up? But anyway, that's how you would do it if you were solving it. Let's redo this problem conceptually using instantaneous center. So you go down here, and I've already done it ahead of time. And to draw the picture correctly, this needs to be on this side over here. So let me do that. Oops. And move it over there. Come on, stay. There we go. Okay. So we know this velocity is going up and down, and we know this velocity is going at perpendicular to that at 45. So then you draw your lines perpendicular, and there's the instantaneous center. Okay, that means we need to find this distance here. Okay. So that distance there is 0.75 cos 13.6. And that comes out to 0.384 meters. Okay, you need to find, so it's not going to be super easy. You need to find this distance here. Huh. Let's see. Let's put in all the angles. We know that's 45. We know this angle is 76.4, which means that angle in there, because three angles inside a triangle, 45, 76.4, that adds up to 121. Subtract that from 180, and you get 58.6 degrees. We could use law of sines to get everything. And I just don't feel like doing it, but you can get this distance and that distance. Let me start it out for you. So 0.75 over sine 45 equals, let's call this d to c, and this is the distance to b, equals d c divided by the sine of the opposite angle equals d to b over the sine of its opposite angle, 76.4. Oh, I'll just go ahead and do it. dc equals 0.782 meters, and d to b equals 76.4 degrees, 0.743 meters. Let me double check both of those. And 72, correct. And 0.743, correct. Okay, and then all that's left is that omega equals the velocity of b, which we said was 2.5, divided by the distance to b, which is 0.743. And once we got that, we can get the velocity of c is omega times the distance to c. But again, something's not right with this. The velocities don't work out right. This would give us the correct velocity of c, and then we could solve for omega bc. I think that's not right, and we could solve for that. Anyway, this is how to solve the problem using instantaneous center. It involved quite a bit of geometry, but there you go.